Hi, welcome to Linux channel. See, one of the key aspects of becoming a network software developer, as I discussed in many episodes, is just not learning some user space socket programming. It goes beyond that. If you want to become expert, especially low level network layers, you need to get into kernel space and stuff like that, because that's where they are implemented. Say for instance, IPv4 TCP stack, UDP stack, whatever it is. I mean to say the whole IPv4 stack, and as a part of that, TCP, UDP, and IPv4 layers actually. So besides that, of course, you need to discover application layer protocols and various things like that. So as a part of it, you start your journey with user space sockets and then get into kernel space, and also besides learn about network protocols and various layers and stuff. I'm just not talking about these OSI layers. I'm talking about the various levels as you put across your headers, the network PDU headers, and build the whole suite. Okay, that's what I'm talking about. And as I discussed in my earlier episodes, you can explore how an FSM is made, how a protocol parser is made. I have done these videos quite long before, so you can search as the Linux channel, and you can find these old videos of mine. See, besides that, this episode I want to discuss about let's fundamentally understand about the aspect of sockets in network programming. I'm again talking about the big picture. It's just not about your user space or user application sockets. Actually, I'm just not talking about the regular sockets. Say for instance, you can search as sample socket TCP, something like that, and then you will get it in a sample C code which has this socket server and socket client. I'm not talking about this, so I'm talking about fundamentally what this is. As you do in user space, how it transfers or how it translates to the kernel space, and you need to see this connect. Okay, see, a user space socket APIs allows you to create this context in the kernel space. As you do this in the user space, please note, you can see here, you come down and you open this socket instance, you get this file descriptor, and then further you define various attributes to this socket data structure, as you see here, sockft, and then you associate those attributes to this data structure, and it will build that whole socket context, and then it is ready for actual transaction, which is transfer and receive operations. And then finally you do a close of that descriptor. If you don't do that, then kernel will see, and then it will gracefully do that sort of garbage collection. Okay, so nevertheless the socket will get closed even if you fail to do this and kill this process or this application. Okay, so that's what happens. So as you do this, you are actually instructing the kernel, because in Linux the kernel is a monolithic kernel, so nothing happens this in the user space. You are instructing kernel to do this, create a socket instance, and then it prepares that all the components which are responsible further. As you do it transfer, okay, either a receive or send, as you do this data transfers, it will build that respective protocol layers and stuff like that, because in user space you just give the application data or the application layer data or the headers, and then this will be encapsulated further within a TCP or UDP header, and then that further gets encapsulated within a IP header, and then finally a L2 header or Ethernet header, and then it goes out as a frame. So whenever I say a frame, which is a PDU which is going on a wire, which is essentially an L2 aspect, which is not technically a packet. Okay, whenever you talk about frames, which means that something which is going on the wire, which means the core L2 frames actually. So that's what. So this converts into that. So who does that? It is the kernel which it does that. Hence the connectivity as to what extent you are interested. You are only interested in working in user space, your limitation lies over here. You can only play with most of the times application layer protocol development as a part of network software developer, and you can go a step beyond. Sometimes you may have an entire TCP suite or entire network stack in the user space as a part of DPDK, or in some level, or some framework you can do that in user space. Say for instance, in the case of Toffee, I do these days process the packets in user space. So I handle network and transport headers, everything in the user space, and I just give to kernel like a raw socket, and kernel just sends these frames. I receive the frame, everything I do in user space, and send those frames. So kernel doesn't have any idea whether these are IP frames or anything. It just gives to user space and forgets it, because that's how I have set up my stack, so that bypass everything. Whatever comes in the kernel, give to me in the user space. Toffee modules, the Toffee modules does that stuff, and then it gives back to the kernel, and kernel sends them out. Okay, this is what happens in the case of Toffee. So it's a good example where the whole stack is in the user space, which is capable of processing network and transport headers, and as well application layer headers and stuff like that. But if you think a traditional use case of sockets, which means that you create you do any application layer protocol, you just send it out via TCP or UDP APIs through the socket APIs. TCP or UDP transport via socket APIs, and it gets taken care by the kernel stack. Okay, so hence you can bifurcate something like this. Actually, let's just bifurcate. This is your kernel space, and this is your user space app. Let's put it in a different color. So these are various user space app. Let's, for instance, we think this is a networking application. This can be a browser, it can be anything. Okay, this can be a browser, or this can be some sort of a Zoom app, right? So something like that. So essentially it is going to open a socket. In the case of browser, it is going to open as a socket client, etc. So since browsers mostly use UDP, except an exception, the quick protocol, if it initiated via Google Chrome, it is an UDP, otherwise it is a TCP. So it creates a socket, and it is browser is always going to connect to some remote HTTPS file server. So naturally browser initiates a socket client, and it is a TCP socket client, and it sends that data out. Okay, so before that it prepares and packs all this application layer stuff, and if it is TLS based, it has to take care of, besides HTTP, the TLS aspect also, and then it has to initiate all the stuff, and it uses as a transport protocol the TCP in the case of the regular HTTPS or HTTP, versus in the case of quick protocol it uses the UDP as its transport protocol. So you just understand the transport service is just like we choose a courier service. You can use UPS, you can use FedEx in case of any abroad shipments. They are quite easy to handle, and same way you may have some service locally available in every country, and also you may have a government operated service as well. Say for instance, in India we have India Post, in UK you have something else, US you have something else. So I think Royal Mail is from UK, so something like that. So you use a transport service, and then you can send it out. Same way the application layer protocol, you choose a transport layer, and then you can send it out. So hence the whole context or the big picture of socket is to handle these transactions. Okay, to handle these transactions, so that what you initiate in the user space is also the context is maintained in the kernel. So the kernel knows, okay, this something comes, how to handle. So you can have multiple tabs. A browser can have many tabs. As you can see here, it can have many tabs, and it is going to initiate many socket connections per tab, because it will have various resources, some image over here, some JavaScript over there. To download all these resources, it will open many sockets, multiple sockets. Hence, to track all these things, you need a context maintained in the kernel which is also maintained in the user space, and whatever you initiate in the user space, it is actually maintained in the kernel space. So this something you need to fundamentally learn if you want to go one step beyond and you want to go more as a systems network software developer and not just a basic fundamental application network software developer. So there is a distinction. So how deeper you want to go? So you want to go much at low level layers such as L2, L3, L4 and stuff like that. Definitely you need to go into the kernel space. In the case of Linux, if it is some other operating system, sometimes it depends the network stack or network subsystem maybe in the user space as well. So we just take Linux as an example. Linux is a monolithic kernel. In the case of Linux, the IPv4 stack is in the kernel space, hence we need to get to the kernel space where these socket instances are actually maintained, which is actually created from the user space, which is actually maintained in the kernel space. So hence you find in the kernel code, say for instance, last week I was doing some or going through some MPTCP stuff, and I just out of curiosity I thought, let me explore the MPTCP stack in the mainline kernel. So when I just gone over here, net, and then you will find MPTCP over here, and you should able to find various files associated with this stack. So MPTCP allows you to split a regular TCP into multiple substreams or subflows. I'm sorry, it's not substreams, it is subflows, and then you can fire this via some sort of a multi-WAN router or a multi-WAN device. It can be even a laptop as well. So this is a unique thing about MPTCP. So as a part of it, MPTCP also maintains a socket context to maintain its own subflows. So you can open one of this file and say for instance we open the main data structure, which is this MPTCP sock. As you see here, this is the socket context of that MPTCP protocol. So we open this and we will find this protocol.h file which has the main data structure. As you see here, MPTCP sock, and it has various member variables to maintain that context. Hopefully sometimes we may have the main sock or the socket which is a part of the main Linux network subsystem will also be attached over here to know the context, or this may be attached over there to know the context. So it's just like you have pointers in C. You have just you have a reference. You just take a reference so that you know that whenever it is needed, you know that it is originating from which major socket actually. So this is what it is. Say for instance, besides this, we search as socket or sock data structure, and we see if anything we find. See, we can find here include linux net.h, and you can see here this is the main socket data structure, as you see here, and you can see there the state and various other things. And so you have various variants or subsets of these sockets of different stack as well. And as I said, one example is this MPTCP sock itself. This maintains the sock context of that MPTCP stack versus this is the main socket stuff. So now if you want to investigate what is the socket status, what is it happening and all, of course you can do some kernel level debugging, which again sometimes I discussed in other episodes, which I just don't want to discuss now. But besides, you can do something like netstat, commands like netstat, and use various other variants of netstats. Okay, so you can do netstat minus L. It shows few things. Netstat, in fact you can search netstat and it will show various variants of netstat. Okay, you can get information specific to TCP connections, UDP connections, and stuff like that. So netstat examples, something like that. Let's take netstat examples. Yeah, UDP port, which is listening UDP ports, which is anyway you are getting it with netstat minus L. which shows both TCP and UDP. Let's see anything besides that. We get listening TCP, UDP, all Unix listening ports, statistics per port, so -s, netstat -s, yeah, it shows this. And besides showing statistics, displays promiscuous mode, routing -i, kernel table, netstat information stuff. Yeah, let's take for example some other netstat. Actually, you can also search as netstat active connections, netstat -a, which shows all these active connections. So as you can see here, it pulls this, but apart from that, you can also use any sort of kernel debugging tools, ptrace and stuff like that, and then get the data structure, dump whenever a API is getting called and things like that, as well actually. So this way, if you are a beginner, just try to map that flow, and of course you have this other data structure, which is this sock data structure, as I was telling before. As you see here, it is in net sock.h. So open this again, you will get some overview from the kernel documentation. You can see that they have documented before this data structure what each member variable is, what is this whole data structure is about. So as you see here, it is network layer representation of sockets versus this socket is a general BSD socket. So something like this. So this way you have an entire accounting system. So whenever you open a socket, it's actually the kernel providing the service from the backend. It is not something you do in user space. You just do this, send the data, it comes to the kernel space, kernel calls, kernel automatically does this copy from user and gets it from kernel user space to the kernel space, and same way copy to user. Whenever there is any RX operation or receive operation you do, it gets from kernel to the user space. Of course, the kernel gets it from the NIC card if it is from a different system, or if it is from localhost, it gets it from that loopback stack, and then eventually it comes to the socket layer. So this is what happens. So if you are a beginner, just go through this data structure, and also you can go through various APIs associated with this. See, as you see here, sock create, and here you can do a kernel level debugging. As you create a socket in the user space, just close all the applications, don't keep anything, and create a test socket via some code like this, using some code like this, create a socket, a test socket, and then see what the dump you are getting it as a part of kernel debugging of that API. Okay, so this way you can do that, and you can find. If not, if you have more patience, sometimes like me, my approach is always I do a print statement, and then I compile the kernel, and then I test it what it exactly shows the way I want it. So the reason I do that extra level of debugging is I can display literally anything rather than limited by some sort of debugging tool. So I can do anything over here. Say for example, this create socket. As you see here, it is calling this wrapper. This itself is a wrapper. This is calling this API sock create, and as a part of sock create, this is the main API. So creates a socket. So here you can put any sort of print statements and print the socket file descriptor ID, and then once it is printed in the kernel logs, we can also compare it with user space code over here. As you see here, sockft is just an integer context. So you just print this in user space, what is the number you get, and you can cross compare with the kernel sock create, the main API. So it could be this, or it could be something else buried within. Okay, again, these things not always I dig down or sometimes even though I do, sometimes I do tend to forget. But if you're working something on this, you can generally approach this way and see fundamentally how it binds whenever you do things in user space, how it establishes this link between the kernel space, the actual thing happening in the kernel, versus what you get it in as a part of services from kernel to the user space applications. So hope this video gives that big picture. If you have anything to discuss, be in touch via mail, or if you have anything to discuss small, you can discuss in YouTube comments as well. So thanks a lot for joining me. Stay tuned. Have a nice day. Bye bye.